Yeah, Moses, thank you for the introduction, and we really have to change gears now. And before I start with the talk, I have to give you some explanation. When we started to talk about this conference, Alexander asked me if we could fit in a new topic like astrophysics and astroparticle physics. And I told him, look, you are the host and you have a lot of freedom to do whatever you want, and it does not really fit the topic, but there is always some connection, and and if you want to do so, I can even contribute with a talk, because since 2002 I'm part of this collaboration that is shown here on this transparency here. This is the CERN Axion Solar Telescope, and axions may be a large part or some fraction of the dark matter where we do not really know anything about it. Okay, and unfortunately this session did not come true, but I was the one left, and obviously the organizing committee was not strong enough to tell me to get out of here and skip the talk and leave the time for something more serious. But anyway, I think you may enjoy it. Let's talk about dark matter. And in our universe, it seems to be true that if it is not dark, it does not matter. And if we look at the sky, we think that those interesting objects here found by the Hubble telescope, that are the interesting parts. They are interesting indeed. However, they do not matter much to the universe at large. And so we have to look at the dark spots where we do not see much. But what can we do? And strangely enough, what we do is pointing a telescope to the most brightest place in the neighborhood of our cosmos, that is the sun, and looking for dark matter. This is a paradox, and I hope at the end of this talk you will understand a little bit of this, why we look for dark matter in the interior of the sun, where it is very hot. Okay, so these are some of the topics that I want to address if time allows. Let me start with some kind of introduction. This transparency shows you our current understanding of the universe. And what we seem to know is that this little piece here, this are we. This is matter that we investigate and that we understand at least a little bit. But this is only 5% of all the matter, of all the energy content in the universe. There is dark matter, this is almost 30%. We do not know much about it. We know it is there, but until now we have not detected it. And even the largest part of it seems to be the dark energy, where we know even less about this. Okay, but this seems to be the knowledge we have about the universe. And now you ask the question, or we try to answer the question, how do we know that it is like this? Well, and since it's a difficult topic, we usually have to go back to Einstein, at least to 1905, when he wrote his 5 papers, and one of them, of course, was about special relativity. And you can think that he worked hard until he found out that the energy is equivalent to mass, and there is just the speed of light in the square in between. So this is special relativity, but Einstein did not stop here. He went from special relativity to general relativity, And of course I cannot give a very deep introduction into general relativity. Of course also I do not know too much about it. But what probably many of us know is that one predictions of general relativity is that light is attracted by big masses, and so this picture shows here. So if the light comes from this star, it is bent around the sun, and if we look with a telescope, we think that the star appears here. This experiment was done by Eddington I think in 1980, and this was first real proof of general relativity. And in general, we like to think of it like this, as in this picture. We now talk about space-time, so our usual three coordinates plus the time. And well, if we have to draw a picture, we draw it like this here, and you see that mass just changes, bends or curves the space-time. And this is actually the outcome of the Einstein's field equations. And now I want to go with you a little bit through this and like to imagine how Einstein arrived at his field equation. Well, in physics, equations are very important, and everybody knows that an equation has a left-hand side and a right-hand side. And of course also Einstein knows this, and he was thinking, what should I put on the left side? If you think of your undergraduate physics, when you try to explain wave propagation, in a wave equation, you usually have on one side a second derivative of the space coordinate, which we still remember that the second derivative gives the curvature. And on the right hand side there is the second time derivative, which has something to do, or can have something to do with energy. So since electromagnetism was known, and the equations there, Maxwell's equation, and the potential of electromagnetism is the same as in gravity, at least in the formulation. So Einstein came up with the idea to write on the left-hand side of his equation the geometry, that is the curvature of the universe, and on the right-hand side he puts the energy contents, and with E is mc squared, it is also the mass of the universe. So this is basically what the field equation means, and not everybody can understand this immediately. We in physics have a short writing and using mathematical formulation, this arrow is too much there. So we put in some Greek letters there, and this is an equation. Actually, we have to understand that on the left-hand side we have the geometry, and on the right-hand side it's basically the mass of the universe. Actually, these are 10 coupled partial differential equations. So it's a little bit difficult, and there is no general solution. A couple of special cases we know solutions, and Einstein derived this equation. Actually, he tried to compare it with reality, and these equations have only dynamic solutions, and since everybody at that time thought our universe is static and eternal, he put in another factor. Something is going wrong with, okay, but I do not have too much equation. He put in this lambda constant, and today we associate this with this cosmological constant with the dark energy. Okay, but now as an experimentalist, you have to do something. So first you have to find out what is the geometry of our universe. It can be flat, it can be curved, it can be closed, whatever. So you have to try to measure it. And a simple way to measure it, we learned even at school, in Euclidean geometry. If you live in a plane world, you draw a triangle and measure the angles alpha, beta, and gamma, and if they add up to 180 degrees, you know you are in a plane geometry. Of course, you know it's different on a sphere. If you start to walk from here, make a 90-degree turn there, and come up, and so here you have more than 180 degrees, and this tells you you live in a curved space. If you are in a form like a saddle, it will be less than 180 degrees. So this is a way to determine. But how do we determine this in our universe? So to make a long story short, you have to think of the largest triangle that you can draw in our universe. And so you try to look out into the universe as far back as possible. And how far can you look with optical or electromagnetic means? You can look not quite to the Big Bang. You can look only approximately 300,000 to 400,000 years after this, because at that time the universe expanded so much that it cooled down, that the electrons were captured by the protons, and suddenly the universe became transparent. So this was the time of the last scattering of photons. And today we see this if we look to the cosmic microwave background, and this is a picture of this. This is the Planck mission. And now a usual professor asks his student, well, look at this map and tell me how large the clusters are there in the cosmic microwave background. What you see here is minute differences in temperature. So the student or whoever designs a clever program, and he comes up and he plots the size. You measure the size of this cluster and plot this, and here is a scale. And what this plot shows you, that most of the clusters have an angular extension of 1 degree. This is, if you look into the sky, about this. And 1 degree, what is this? Well, it comes up to the fact that this is exactly, it is consistent with 300,000 light years. Now you have to imagine you are a little piece of matter 300,000 light years after the Big Bang, and they tell you you have to collapse to our galaxy, to the Milky Way. How do you know where you go? And you have gravitation, and so after 300,000 years you can only talk to another particle not more far away than 300,000 light years. So this is what you see here, and you have this triangle. 1 degree corresponds to this, and if you live in a flat universe, you see this 300,000 light years here, and if you were in an open geometry, it is this and this. So you measure the angles, and you come up with the fact that our universe is in general flat. So the left-hand side of this equation tells you we live in a flat universe. Now the right-hand side of this equation tells you you must have some mass to achieve this. And now we have to put our universe on a scale and measure it. And well, how do you do it? Well, the first attempt is like this. You go up there and count the stars. You know the average size of the stars and count them. And if you do this very clever, you come up that you have only 5% of the mass that is necessary to make the universe flat. So this is not enough. Maybe we are missing something. And we are missing indeed something, and again Einstein tells us this. I think he wrote this paper in 1936, and he wrote to the editor, and I read it out. Let me thank you for your cooperation with this little publication, which Mr. Mandel, an astronomer from Austria, squeezed out of me. Because this person looked into the general relativity and said, well, the light must be curved, there must be a focusing effect, please calculate this. This is the result of the calculation. But in order to really focus, you need a lot of mass. And so Einstein thought this is not important. However, today we see these nice pictures from Hubble. This is you see here like Einstein rings. So a very distant star, the light from this is focused by gravitational effects, and here it is shown even more nice. So we have this gravitational effect and focusing effect. And today we have wonderful computers. We can calculate the distribution of mass in order to give us these kind of pictures. And this is an example, and what you see here, these are the stars that we see. But most of the mass of this focusing galaxy is in between, and this is matter we do not see, and this is one example of dark matter. So there is something out there that acts gravitationally and we don't see it. This dark matter goes back to 1932 and 36 to Zwicky and Schmidt. And now since we have a lot of these Einstein rings and focusing, you can calculate the average mass of a galaxy clusters. Then you start to count again. Okay, I make it a little bit easy, but if you do this, you come up to 30% of the mass of the universe. 30%, but 70% are missing, and for the missing 70%, we recently had the Nobel Prize for discovering of the dark energy. This has to do something with that people find out that distant galaxies are not only receding from us with high velocity, but that this speed is increasing more and more, and this is due to this cosmological concept. So now I tried to give you an idea why we think our universe looks like this. And now I want to address this a little bit, and this is our collaboration, and we are looking for a special piece of dark matter which we call axions. And these axions are very special because our colleagues from nuclear physics like it. Many of us remember that weak interaction violates the CP symmetry, charge and we always wondered why strong interaction doesn't do it, and no experiment until now shows CP violation in strong interaction. And so Peche and Quinn came up with an idea to have a new symmetry which is spontaneously broken. Let me say it in more easy words. There is a field that suppresses CP violation of strong interaction, and the field particle associated with this is is an axion. This term was made by Wilczek, and actually axion is a detergent that you can buy around CERN, so you get away with stains, and this CP non-violation of strong interaction is a stain in the COD, and this should be solved by axions. Axions are similar with their quantum numbers to the neutral pion, and Primakov in 1951 suggested this process for the decay of the neutral pion in two gammas, and the same effect should work for axions. So if you do this, you have a photon. You have two photons. The second photon can be a virtual photon from the electric field. They can couple to an axion, well, now I adjust. So this is the effect. And if we go back in time in the evolvement of the universe, here, where it was very hot, you have very many photons and protons. So at this time, many axions could have been produced by this effect. And so the idea to measure it today is we look at the sun, and in the interior of the sun, where fusion takes place, photons could couple to an axion. They do not interact, they come out, you build a detector, you reverse the project. We don't do it with an electric field, but with a transverse magnetic field. And so the original photon here will come out here and will be detected with an X-ray detector. This is the formula. The physics is here in the coupling constant, and the experimentalist must know you need a strong magnetic field as long as possible. So this is the detector. And going back to the dark matter, if we determine this parameter, the coupling constant, we could go back and calculate how many axions have been produced shortly after the Big Bang. And now why CERN? CERN built this LHC, and before they did this, they checked how these magnets could work. The CERN magnets are bent a little bit because there is a 27-kilometer circumference, but when they did the prototype magnets, for cost reasons, they made them straight. They had two of these magnets on the junkyard of CERN. They were discovered there by our collaboration speaker, and he went to the CERN general manager and said, well, I want to do this experiment. I want your junkyard magnets. I built an astronomical mount. We have a collaboration, put some detectors here. This experiment doesn't cost you anything, and this is exactly the way you address management. You make an important experiment, it doesn't cost you anything. It costs CERN 1 million per year, Swiss franc, for the cryogenics. But nevertheless, it's not an expensive experiment. So what you expect to see is a spectrum like this, and this is in principle the black body spectrum corresponding to 16 million degree. So the photons should come at 3 keV up to here, so you have to have a detector that is good in this area. And this was our idea from Darmstadt. I come to this, we built this, we had this X-ray detector, and put it to the CERN experiment. So this is cast, this is the LHC here, the CERN, the Geneva airport, the CERN laboratory is here. We have here our experiment. So what we have is an X-ray telescope and a CCD camera, and we expect our signals to be here. So we test this, and since 2002 until 2015 we did a number of runs and analysis, and getting better and better with our our precision. And well, this is the data from one of the runs 2009 to 2011, and here should be our data. And of course, what we do, we have this this magnet pointing to the sun, and it is on this astronomical mount, and in the morning and in the evening. So we cannot follow the whole day the sun, because it's a super conducting magnet, 50 tons, and you cannot point it up there. But we can point it from -8 to +8 degrees and move it, so we can follow the sun for 1.5 hours in the morning and 1.5 hours in the evening. So the graduate students have to be there, and I get up later, and in winter I go skiing, and in summer I go sailing, and in the evening I check the data. It's not quite like this, however, well, we do this, and when we do not follow the sun, we measure the background. So what you do here is you do this and subtract the background, and then you have data wobbling around zero. To make a long story also short, here is we did not detect an axion, otherwise our collaboration speaker would have the Nobel Prize already. But what we did is we were measuring here in this area, and we measured the coupling constant, and the coupling constant is smaller than this value. This we can say. So we have an upper limit for the coupling constant. And of course now we entered already this interesting field where we are close to the limits that are set by other methods. So it would be nice to go much beyond this, and our young people of course have the idea to build such a detector, a big magnet, but this is a very expensive project, and usually these projects take 10-20 years. I may not be around to see it, so I'm not so interested in this. But in the last 2 minutes I want to come to a mystery, the sun cycle. 11 years. Right now we have very little sunspots. No one knows how the sunspots come about. However, with this 11 years, this might have something to do with with Jupiter and Earth matching up, and Venus all 11 years. But it cannot be gravitational pull. Most people are convinced of this. However, we had the idea that if we have streaming dark matter, this constellation may focus an axion stream into the sun. They may convert to radiation and do something there. Since this gravitational lensing could enhance the flux by a factor of 10 to the 6, this could have an effect. Well, and now we are close to our subject, because if you want to calculate the gravitational lensing, you have to know how Jupiter is made of, for instance. You do not need it too exactly, but the better you have it, the better it is. And one of our topics in high energy density matter is try to find out the equation of state of Jupiter. And of course, in these calculations, we put in the best equation of state of Jupiter that we have from the Ronald Redmer group in Rostock. So you see, the fields may be apart as much as you think, but they can be related. So the last word I want to make is dark matter is also a field, and the field particles in some theories show up like chameleons, which means they can have different kind of masses. And now we want to install in our cast experiment this device, an optical cavity with a membrane in, and if the chameleons from the sun hit it, the membrane wobbles a little bit, and this can be detected in this cavity. And this experiment will start very soon. So again, and now I'm at the end, photons can be, in some cases, signs for dark matter and dark energy. Thank you.
Nice talk. And any questions and comments?
How small, I mean, at what point do you say there are no axions? I mean, if you push the coupling constant down to what level does it become?
So it's in that these units 10 to the minus 10, and this is just at, I have to make a remark. If these axions are produced and they go out of the sun, this is an energy loss of the sun, right? We think our models are quite good to determine the lifetime of the sun, so it must be within. There are stars that burn helium that do not live very long, a couple of million years, and since they are there, and we think to know how hot they are, how much photons there are, so seeing these stars gives an astrophysical limit on the axion production. So the coupling constant must be lower than this. And we, with our experiment, are just touching this limit, and we do not see an axion yet. So the coupling constant, you know, it may be just a factor of 2 smaller, but it may be a factor of 200 or 2000 smaller. We do not know. So we want to get more efficient, but there are other experiments on axions and dark matter too, and until now they don't see anything. And this is a mystery, and if IceCube and all the other experiments don't see anything within, let's say, 10 years, maybe we have to think about the underlying theory. But as an experimentalist, I don't care. I check it, and if the result is this or this, then the theorists have to worry about it. But I tell them, I'm sure this is my data, the coupling constant must be even smaller. Maybe there is no. Then someone has to come up with an idea.
Over there.
Can you comment about the magnetic field you need to have an effective measurement? How large the magnetic field has to be?
Yeah. Can I help you? Well, I showed the formula, and except the coupling constant, there was B square and L square. And at the moment we have an LHC magnet with 8.5, let's say 10 Tesla, 10 meter. And we expect at the level of 10 to the, what I showed there, 2 or 3 events per day. And so we must be lower. So the next step, CERN is thinking about 50 Tesla magnets that would help. So I think one has to wait until these magnets are available, because just for this experiment to build a new magnet, it's difficult to get the funding.
So this magnet needs to be homogeneous and constant
Yes.
over your
Yes.
distance.
Yeah, it's very homogeneous over 10 meters. The point is, we do not know the mass of the axion. And this coupling process is a coherent process, and if the mass is high, then you lose the coherence, which means that photons are faster than the axions, and they lose coherence, and this reduces the effectivity of the detector. So after some time we put in helium and helium-3 to slow down the real photons, to have at a special mass range again the recovery of the detector. But anyway, now we have to have larger magnets or something quite different.
Another question. When you showed
Can you speak to?
Yes. You have shown to us a Feynman diagram with an axion, a photon, and you had a double line. What's the meaning of that double line? You had a virtual photon, a real photon, and an axion.
Yeah.
And parallel to the upper lines, you had a double line at the bottom. What's the meaning of that double line?
Probably I don't know, but let's see.
Forget.
Okay. So actually we are a little bit behind time, and we have a